And this is a kind of recap of what we have learned before. So we have two metals, which is the copper and the nickel. Okay, and you can see that for pure it is straight line. So when it is mixed, it becomes slanting due to the difference of melting point or melting temperature. So we use that to construct a phase diagram. So what the result will be, like in the left, okay? And this area is the liquid plus solid. And this is how the isomorphous binary phase diagram looks like. Isomorphous binary phase diagram looks like this. Okay, so there are no formation of second phase. So what I mean by second phase is like in this case, how no matter how much you add, you will still it will still exist in the same homogeneous phase, but if the material is not completely soluble, it means it has a partial solubility. What happened when you add this solid into the other and you heat up? So what you get, you have it will dissolve for some times, but eventually there will be formation of second phase forms of precipitate. They will have second phase, and this is the second phase, and then this is the first phase. You will have a contrast of materials on the surface, and isomorphous system is this one. It don't matter how much you add, it won't form any second phase. That is for the isomorphous system. So you see, yes. Okay, so I'm not sure. This one I have already taught you guys. I have some feeling that I have talked about this one already. But okay, let's just go because tomorrow we have some time. All right. All right. So, for example, if you have 50% of copper and 50% of nickel, okay, what is meant by 50% is the atomic percentage. And atomic percentage, you will have to measure it by mole. Okay, the same mole, you use the same mole of copper, the same mole of nickel, and you put it together and you heat it up, so they will form a liquid corresponding to this line. Okay, corresponding to this line, they will form liquids, and then when you solidify or you cool it off, it will start to solidify at this exact temperature of 1330, following this line. Okay, so you can see here complete liquid, and then this line, the nuclei start to form. This area there is a mixture of liquid and solid, and when it exceeds the solidus line, the crystallization ended to become complete solid. And yeah, I think this is one of the important idea behind the phase diagram. Okay, behind the phase diagram, you have to be competent in using this tie line. Okay, what is meant by tie line? For example, you have this amount 50 and 50. Okay, you mix together, you heat up, and then you get this molten metal of molten alloy, and then you cool it off. Okay, and it at this temperature we take at 1300 degrees Celsius. So from this phase diagram, we know at this temperature the phase will be liquid plus solid. Okay, this is the use of phase diagram. First, we know the phase. Okay? We know about the phase. All right, and then using this, because you have this point, so what you do is that you draw a line. Crossing the liquidus and the solidus line like this. Okay, and I just want to emphasize actually this red arrow. Okay, the red arrow, you just draw the line. Okay, you draw the line, and the point which it touch the liquidus line and the solidus line is the important point. Okay, so what we are going to do here, okay, now we know at 1300 degree these materials exist in form of liquid and solid. Okay, this solid, how is the composition? That is where we use the tie line. Okay, so when you draw this tie line, at this point, when you extrapolate it to this x-axis, you will have the exact composition of the liquid. So meaning to say that if we have this as the axis of copper, okay, so you have 50 something of copper, okay, 55.25, let's say. And at the same time, you can extrapolate it to the nickel, which is the 44.75. Or you don't have to extrapolate it because the total will be 100. So you just take 100 and you subtract it by 55, so you get. All right. So if you want to know the composition of the solid, you have to refer to the point where the tie line cross the solidus line. So you have it here, you extrapolate here, and then you know that the copper should be 43 something, 40 something, below 50, yeah. So you have to be careful. Actually, there is scale down here, but I think this is for the presentation purpose. We just take it, we just draw it like simplified. Okay, so you could know that the composition of the solid is like this. Okay, so are you guys clear with that? Boleh faham tak yang tu? Okay. So that is number one. Okay. Now we go to the number two. This is tie line is the first one, and this what we call lever rule. This is the most important, one of the most important thing to understand in understanding the phase diagram. So, okay, just now we said from the phase diagram, we could understand for the material at a certain composition, okay, when you use the total, okay, I think you need to clarify on that. Okay, this one, you see the total of the material, okay, total amount of material is 50 to 50, okay, 50 to 50, right? This is this line, this green line indicates the total is 50 to 50, but at this temperature it exists in two phase, okay, it exists in two phase, and each of the phase is given by the tie line which we see just now, okay. So the total is 50 to 50, but the liquid, for example, in this case, have copper rich. It has more copper. Okay. For the solid, it has more nickel. All right. All right. So we could also understand from this that this is because the solid. Why solid have more nickel? Because the melting point of nickel is higher, so it solidify first. So it has more atom in forms of solid. Okay. So that is I want to differentiate between this this total amount. 50 to 50 is the total amount. Okay, but each of the phase, the amount is different. The amount is different, but the total amount is 50-50. Right. So level rule tell us we know, okay, at this temperature, right, it is the material is in form of liquid and solid. So the level rule tell us how much is the solid, how much is the liquid. Okay, what is the percentage of solid, what is the percentage of liquid? We know the fraction of the phase. Okay, the fraction of the phase. So how to do that? Okay, from the tie line just now. Okay, from the tie line, we know the composition. Okay, fine, the composition is there, but we want to know how. Okay, let's say how much is the volume of this one? How much is the volume of this one? Fraction. How many percentage? Okay, we have there. So what you do, okay, from the tie line, okay, you divide into two, okay, from this area, from this line to the center, or to our exact composition. If we can label it as A, and the other half is B, okay, so we have the total length A plus B. Okay, the total length is A plus B. A plus B. Okay, first, I think you yep. You tak payah tengok lagi. Oh, before you okay, before this, okay, I want you to okay, so we have the tie line here, so I just magnify it here. So we have this one, we have this line. Okay, you have this line. then you have this line, this curve, right? Then you have this. Okay, this part A, this part B. Okay, so you have the total length is A plus B. Right? So if you want to know, okay, this is the liquid, this is the solid. If you want to know, the amount of liquid, you don't take A, but rather you take the opposite side. You take the B, okay, B, you divide it by A plus B. So L, fraction of L is B over A plus B. Fraction of S or solid, you take not the nearest one, but the other way around. Okay, you take A plus B, and then you multiply by 100% lah. So from here, you will have the amount of each phase. Oh my. So from here, you will have the amount of each phase. You see, from the solid, okay, the fraction of the solid is the A here, okay, and from the liquid, not this one, but the other way around, B. Okay, that is how you you can see that yeah, or you can use the scale as well. It's no problem. The same. So you can get this. There is in the mixture of the phases of the two phases of solid and liquid, the amount of solid is 45%. The amount of liquid is 54%. So that is how you use the lever rule, right? So, okay, let's see the microstructure. So this is the point where the nucleation start to occur. Okay, the nucleation start to occur, and yes, all right. Uh, at the that okay the am I disconnected? Terus lagi ke? Anjir Korea. Zina. Boleh dengar? Saya punya suara boleh dengar?
Boleh sir. Lag sikit.
Oh. Berapa tak dengar? Oh, Korea. Macam lah. Boleh dengar tak?
Boleh sir.
Oh, saya tak tahulah dia punya, dia cakap size of the call besar sangat dan saya nak share window pun tak boleh sekarang ni.
Oh, salah sir.
Bukan susah juga, susah betul.
Ah,
Sekejap. Boleh tak? Nampak?
tak nampak sir.
Ha?
Nampak sir.
Okey, cantik. Okey. Apa benda tadi? Kat mana tadi kamu dengar? Kat sini dengar? Yang sekarang?
Dengar sir.
I mean tadi yang mula putus dekat sini ke? Slide
Sekejap.
ni ke? Level rule dah kan?
I think the previous slides are basically.
This one?
Yeah.
Oh, this one?
This one.
This one?
Yeah.
This one,
Yes.
Okay. Yeah. So the level rule, what I was sharing was, the level rule is used to understand, okay, we have this amount of composition, 50 and 50, and we have this 1300 degree, we know that the substance exists in form of solid and liquid, and using the level rule, we know how many percentage of liquid, how many percentage of solid. Okay, that is by referring to this fraction. You from the tie line, you have A from this point, from the point of our composition to the liquidus line, if we regard it as A, and from this point to the solidus line, we take it as B. So what happened? We use the opposite. And if you want to know about the liquid, you take B, the one here, okay? And you divide by B 100 lah, okay? Because we want to do the fraction. If you want to know the solid, how many percentage of solid, you take A the other way around. You take A, okay, this use here, you take A, you divide A plus B, you times 100%. So you get the amount. So this is the calculation, the example of the calculation. So you get from this, the length, you can refer to the scale here, and you measure the length, how's the length, and so you use A plus B, okay. For the solid is this way, liquid is this one, okay. So for the solid, you use the other way around, you use A, okay, use A. So A divide by A plus B, and then you get 45%. So you want to know about the liquid, you use not A but B, okay. You use B, you divide A plus B, and you get the 54%. All right. So that is the level rule. I hope you understand these two concepts of the tie line and the level rule. Okay, now we want to have a look on the microstructure. So you see, using the tie line, for example, we have this we have this material. So yes. We clear it off little by little. We reach this point where the nucleation start to occur. Okay, so from this point, okay, you draw the tie line. Okay, tie line. Okay, boleh? Boleh dengar?
Boleh.
Putus tadi? Yes, tadi putus.
Yeah.
Alright. Okay, so I think you during the level rule, I think this the connection was still okay. Now we come to the microstructure. I was telling you guys that we have this amounts of material, okay, nickel and 50 nickel and 50 copper, and we have this line, this green line. The solidification will follow this green line. So when it go beyond the liquidus line, there will be nucleation. The nucleation will start to occur, and we want to know, okay, the solid. We want to know the solid composition at this very first nucleation. If we want to know the composition of the solid, we just draw the tie line here, and then we see the composition. So in this case, the solid is 37% of copper, meaning that the remaining, which is the berapa tu? 7, 6, 63, 62.5 is the nickel. So you can understand why nickel is more in this very first nucleation, because nickel has higher melting point. So that is why it is more. So when the solidification continue, so you can see that at this point, when if you draw the tie line, the composition will be different. Okay, the composition will change. You see? Okay. For this 43, so if you draw this tie line, you can see that it drops here. Okay, so somehow the copper content is has increased compared to the first nucleation. All right, so when you reach a fully solidified, when you reach full solidification, this is the point, and then you draw the tie line, okay, connecting the solidus and liquidus line. So you get the copper content is different. Okay, sorry. Yes. No. Oh, yes. So you get a different composition for different temperature. Okay, you get the different composition for different temperature. So to illustrate that, okay, so you can see that this is the what happened actually. What really happened? Okay, it looks like this. It has a contour. Okay, because the composition is changing every time the temperature change, and there will be a difference in composition. Okay, and this cause the if this happen, actually you have a segregated structure, means that the amount or the composition throughout the solidified solid, it will not be uniform. Okay, that is what we call segregation and segregate. There is some area which has more concentration of certain element. Okay, so what we do to get to uniform it back, we do what we call the heat treatment. Okay, because this occur very fast. Okay, very fast. that is why there is a different of there is a gradient of composition. Okay, so when we for example when we when we heat it at a certain temperature, okay, when we heat it back at certain temperature. So for example this the solidification, you see, it occurs at this range 1000 something. Okay, so when we heat the product, the alloy at a high temperature but below those melting temperature, okay, the atoms they will diffuse. Okay, they will diffuse and form a uniform structure. Okay, instead of this segregated, you have this dark colored and the bright colored phase. It looks like different phase, but actually it is a different composition. Okay, but it is not in equilibrium condition. Means that it is occur due to the fast cooling. It's not it's not it's not the most stable state. Okay, so to promote that, to promote uh, the actual equilibrium state, okay, the actual equilibrium state, so we do heat treatment. Okay, we do heat treatment, and you can see that from this which has like distinct contrast, you have very uniform. Maybe this black color is only maybe pore or something, but porosity, this is some defect. Defect when you do solidification, there will be defect. Okay, and this maybe you can see the line. This line, you can see this is the grain boundary. Okay, this is the grain boundary. All right, but the fact is this material, when you heat up, it will become monophase, only one phase. Okay, and you can see that when we have different composition or different structure, it will give effect on the mechanical properties. Okay, and this is the example of it. You see the tensile strength, okay, of the material. If we have this amount, okay, so it has the highest tensile, this amount, and it is a trade-off. If you have high strength, you will have low ductility, so the elongation drop here, exact place, due to this trade-off relation between strength and the ductility. But this is just to show you guys that the mechanical properties changes with the change of the composition. Okay. So in summary, all in all, there is we learn about this isomorphous diagram. And from isomorphous means it has only one phase. Okay, no matter how is the composition, and we know that how the phase diagram is constructed using the cooling curve. We know how to use the tie line. This is the lever roll, not the lever roll. Lever is hati. Okay, the lever roll is used to determine the phase fraction. Okay, we came to that now, and microstructure of metal can be predicted from the just now what I was saying, we have those kind of segregation, and it can be avoided if we do the cooling slow enough. We do the cooling very slowly, so we have this kind of like more homogeneous, or we can do compensation by annealing, or we can say heat treatment by promoting diffusion. Okay, and lastly, we have take a look on how it changed the mechanical properties of the material, and that's wrapped up. Aduh, penat je cakap seorang-seorang. Aduh. Dekat mana tadi? Aish. Ai. Hello. Anyone hear me?
Yes,
Dengar, saya dengar.
Tadi kat mana? Yang korang nampak last kali?
Summary, sir.
Oh, ni habis lah semua ni? Tadi ada lah. Masa
Yeah,
saya
last
cakap
year aja.
story. Okay So tak apalah kau macam tu. Boleh Ni dapat lah tadi kan? Mechanical semua ni. Okay
okay.
Okay. Oh, penat. Ingatkan saya cakap seorang. Cakap seorang jugalah. Aduh, tak tahu kenapa. Sekejap. Kita pergi slide yang ketiga. Esok ada kelas kan? Ada test tak esok?
Ada tutorial pagi esok.
Okay, boleh nampak Share slide.
Tak boleh nampak, sir.
Mana doktor?
Okay. Alright, so just now we have learned about the phase diagram of isomorph. Okay. Just now we have learned about the isomorphic system. Now we go to eutectic system or isomorphous system. Now we go to eutectic system. All right. So in this lesson, we want to understand what is eutectic. This system is still a binary phase diagram, which means we only have two main elements, and we want to be able to integrate the phase diagram, and we want to understand the reaction of eutectic transformation. All right. So we go to the introduction. We go by line by line. A eutectic reaction is a three-phase reaction by which, on cooling, a liquid transforms into two solid phases at the same time. A liquid transforms into two solid phases at the same time. Okay, liquid transfer into two solid phases at the same time. Right.
Doctor,
So yes.
tak share screen.
Aish. Itulah banyak kali sangat dia tertutup. Saya pun. Okay. Sorry Thank you. So okay, we go line by line again. So what we were defining was a eutectic reaction is a three-phase reaction. Okay, means it involves three phases. Okay, by which during the cooling, okay, a liquid transform into two solid phases. Not one but two solid phases. Okay, so for example, liquid alloy become a solid mixture of alpha and beta at a specific temperature. So if you were to write here, so we have the liquid, it transforms into alpha and beta. What is alpha and beta? Is solid of different type, different composition. This is what we call different phase. Okay, two phase. All right. And for example, we have bismuth and tin. So we do experimentally, we add bismuth and tin with various composition. We will get something like this, the cooling curve, and we translate that into, we remove the time, translate that into the phase diagram. We will get the phase diagram as this one. Okay, and to simplify that, let's see here. Okay, what we have here, we have the same liquidus and solidus line, but we also have this eutectic line, eutectic point. Okay, so what is meant by all this thing is that okay, so you see first I want you to understand that we have what we have here is alpha and beta. Okay, alpha and beta, and this alpha and beta it is a phase. It is a phase. For alpha, you see that the content of this is the weight of the tin going here. So the content of the tin is very little, and the content of bismuth is abundant. Okay. Okay, so you can see that it said here for alpha, it is bismuth rich with some tin atom inside its bismuth crystal structure. Okay, and for the beta is in the extreme of tin. So we have tin rich with some bismuth. Okay, so these are the two phase which is exist in the eutectic phase diagram. Okay, so in between them, there is a mixture of phase. So it has a little alpha, a little beta, not little some amount of alpha, some amount of beta. So this is what I was telling you guys over and over again. Okay, over and over again. When we have two solid, when we add one of them to the other, there will be limitation. For example, this is the limit. This is the limit. You see in alpha, the tin inside its bismuth means the tin dissolve in bismuth. All right. So when it exceed this line, which is the solubility line, it from only alpha, now it has beta. And if you add, add some is okay, it dissolve, it's still alpha, but you add more, there will be formation of beta. You add more and more and more and more, you get more beta. Until finally, if you add more, the beta will be the dominant one, and the alpha, and it will be tin rich. The beta will be the dominant one, and bismuth will dissolve in the tin. Okay, so that is what the eutectic phase diagram tells us. And okay, what happened? We want to know what happened at this line, at this point. Okay, this point. On this point, eutectic point. Okay, what happened actually was, okay, sorry, not yet. We go little by little. We go this line first. This line. If we have this line, so what happened? At first, it is in liquid form. Okay, and then point number two, this one, we are referring to this number two, this number two with this number two. Okay, so at first it is liquid. Okay, it's liquid, and then at this one we have liquid plus alpha. So we already have some alpha. Inside. Some solid. Okay, alpha. And when we at point number 3, it is completely alpha, completely solidified already. We have alpha. And when we cool more, we have formation small amount of beta. Okay, we have alpha and beta. Let's put the beta with blue, so you get alpha and beta. All right. So see this one from the phase diagram, we know, okay, if we are at this point, this is the phase. We are this point, this is the phase. This point, this is the phase. All right. So if we have that amount, this composition, now we change the composition. At this very point, okay, where we call it the eutectic point, okay, the eutectic point, okay, what happened is this liquid and this liquid, there is no intermediate liquid plus solid. Like this one have liquid to liquid plus solid. But here liquid with at the same temperature, okay, just like pure metal, it change directly into solid. And for eutectic, we have no the definition at the beginning that from liquid it changed into two kind of solid at the same time. This is the eutectic point. And in many cases, this formation of two phases at the same time, it will result in a lamellar structure. Dia jadi belang-belang, jadi lamellar, because it happens so fast. You don't have that time to get together, divide into two large amount or large area of alpha and beta, but rather it occurs in a very short time, so it will have this lamellar structure. So you see that yep, this is how it looks like, the lamellar, the solidification at the eutectic point. So you can from here, number one is liquid. If you were to, so number two is the nucleation start to occur. Maybe some nuclei, you can say that some nuclei, and after it finish, you have combination of alpha and beta. Okay, we have a mixture of alpha and beta. Okay, so this is how it looks like. You can see all these, eutectic point, this maze pattern. Okay. Okay, now we come to the word hypo eutectic. What is meant by hypo eutectic? Okay, you see, this is the eutectic point at the center. Okay, if we have it here, call it hypo eutectic. And what it is all about, it's what we call, okay, when you have, for example, at number one, it is in liquid form, okay, and at number two, the solidification start to occur, and we will have in between, when it pass number two, there will be mixture of liquid and solid. Okay, liquid and solid, right? And the remaining liquid, because this one is not 100% solid yet. Okay, we have ample amount of liquid still, you know. Now the remaining liquid, the eutectic transformation occur, you know, from the liquid to two kind of solid. So you will have eventually this what we call the primary alpha, which solidify first, and we will have the lamellar structure as well from the remaining liquid. You have the lamellar structure from the remaining liquid. This might be the not complete one. The number 4 will be complete lah. Okay, this is the starting point. Number 3, number 4 will be complete like this lah. Okay. Okay. And what happened? It looks like this. So you can see this very big block is the primary alpha, and this you know, if we zoom in this one, you find it is not the monotonous texture, but it has the lamellar structure made up from the alpha and the beta. Okay, so that is hypo eutectic, and if we go to the right, we have hyper eutectic, and the story is the same for hyper eutectic, only it is inverse. So you will have the formation of beta first, primary beta. You have the primary beta with the remaining of the liquid, and then the liquid transform eutectically into this lamellar form, and you have this big block of dark colored, and this the bright colored. If we zoom in, you will have this kind of like not 100% bright, but it has this kind of maze pattern or lamella, which indicates the eutectic transformation. So okay, and then we have the same thing for this one. If you use this bismuth rich, tin rich, so you will get this kind of line, solidification line, and did I jump? No. Yeah, solidification line. So you will get beta, and then upon freezing, upon you cooling off again, you will have this alpha and beta. Okay. Okay, so you can see the difference. This one has more, but this one with more extreme to the right. We have only small amount of alpha plus beta. We have very large amount of beta. And how to determine the phase composition? So this is the same thing that we were talking about. We use the tie line. So for example, we have okay, so we have this alloy, okay, 70 tin 30 bismuth. All right. And from here we know they ask at 250 what is the phase. 250, it is completely liquid. I'm not sure what this. I think this is a mistake. 250 should be liquid. Liquid. There is no beta here. Oh, maybe 150. 150. Yes, I think this one is silap. Okay, 150. 150. 150 here 150. Okay, so it is alpha plus beta, liquid plus beta. Okay, fine, we know the phase. And what is the composition of the liquid? Composition of the liquid. So composition of the liquid, we draw a tie line here, right? And then we check, we expand this one, and then we have the composition. And for beta, you go to the right because beta is here, so we get the composition of beta. And then you want to know the composition of the liquid. Okay, the liquid, you go to the left because liquid is here, so you get the composition. So that is how to use the tie line. Now we want to determine how much is the fraction, how much is liquid, how much is the solid. Solid is the beta solid. So we use the lab rule. We take the other way around. So you get this amount. All right. So phase diagram application, we can use this phase diagram to know the microstructure when we do, especially for this one. The example, we use the lead and tin, which is used as a solder. This is solder. So you need to understand how is the composition. How is the composition? And with the composition, what is the resulting mechanical properties and so on. So it is helpful for us to understand in this case alpha, beta, and how is the ratio and how is the properties of alpha. If we shift a little bit and make more beta, what happened to the solder? Okay, so that is the application or the use of phase diagram to understand the behavior of the material when we apply those combination of two metal. Okay. Right. So in summary, all in all, is you can say that eutectic reaction ni apa adalah eutectic reaction is a liquid into two different solid phase. Okay, that is one thing. And then complete solubility does not exist. Okay, there is a limited solubility for eutectic lah. Okay, and there are four kinds of microstructure that may develop from the equilibrium cooling of alloy belonging to eutectic system, which we have reviewed just now. Okay, so far boleh faham ke? Is there any question? Okay. So I'm sorry to bombard you guys with all these slides. You know, yes, in a very short time because we have been not be able to have a class for quite a long time. So have to compress it and accelerate our class. So okay, I think you guys ada satu lagi slides ni. Tapi saya rasa tak akan habis lah hari ni. So you guys tomorrow ada kelas juga kan? Kelas masa untuk tutorial. So tomorrow we have the tutorial class. So basically I think I will not do any tutorial this week. So I will use tomorrow class as the lecture lah, as a lecture. And yeah, even if we do some tutorial, I think it should not be I think you guys need to concentrate on the test. Test one first, and we will do the tutorial after the test one. For the time being, I think we just complete our lecture, and I think today I have compressed quite a large amount of lecture for you to digest. So I think we just stop here. Even if I continue, I think will not be productive and will not be we will only reach halfway. So maybe tomorrow you forgot again, and then we have to repeat all over again. So I think tomorrow 8 class. Tomorrow 8 we finish off all this phase diagram. Only there's one slide left. Okay,
Boleh.
Okay, so kita habiskan lah benda ni awal sikit. So you guys take some time, you guys digest sikit apa itu phase diagram. I think the content is not